Hello everyone, this is K1 from MBT. In this session, we're going to have a simulation on battery thermal abuse modeling. As you may already know, a battery thermal runaway could occur via different reasons. Among them, internal short circuit caused by physical damage is the most important one, which, for example, as your battery pack may be damaged via an accident. The second one is poor battery maintenance, and the third one is exposure to extreme temperatures, like when you live in a very hot area and your car battery is exposed to extreme temperatures. For a battery, there are several temperature values that define your battery functionality. The normal operating temperature for a battery is 25 degrees. The maximum operating temperature is around 60 degrees, and above this temperature value, several decompositions will occur to your battery. For example, the SEI decomposition, the electrolyte decomposition, cathode decomposition, and above temperature values like 150 degrees, the thermal runaway will occur and your battery will lose functionality. In the Ansys software, in order to model this thermal abuse, there is an advanced tab in the MSMD battery model that uses two models to simulate the thermal runaway. The first one is a one equation kinetics model, and the second one is a four equation kinetics model. So in this simulation, we're going to use the one equation kinetics model, as you can see here. This model has different parameters like alpha, which is the degree of conversion, and other parameters as pre-exponential factor of the reaction, activation energy of the reaction, universal gas constant, which you may already know, the temperature, M&M, which are the reaction order parameters. All these parameters could be estimated via a Fluent provided parameter estimation tool. So in order to start the simulation, for the simulation setup, we have a C-rate value of 1. The time step size for this simulation would be 0.1 second, which is a small value, and it is due to the high gradient of variables, and specifically the temperature values. And the total number of time steps would be 300. So we can guess that after about 10 or 15 seconds, the simulation is done and we can see the results. So now let's go to the Ansys software and start the simulation. So here we are in the Ansys software. We should start the Fluent solver. If you want to know how to create the geometry or the mesh, you can watch the videos on the elementary playlist of the channel, and you will know how to create these two models. So we use the double precision and serial for processing. So as you can see, this is a very simple structured mesh for the battery cell. Before starting the setup, we check the mesh to see if the minimum volume is positive. For the time, we use the transient. And from the physics tab, we enable the energy model to capture the heat transfer and the temperature variation. So if you check the equations under the solution tab, you can see the flow equation and the energy equation are selected. So now we're ready to import the MSMD battery model. So we use define models add-on module, and we select number 8 for the dual potential MSMD battery model. From the models, you can see that the MSMD battery model is loaded. So we enable the MSMD battery model. For the e-chemistry models, we're using NTGK empirical model. The nominal cell capacity would be 14.6 amp hour and the C rate would be 1. The minimum stop voltage would be 3 volts and the maximum stop voltage would be 4.3 volts. As we see in future in the thermal abuse modeling, the temperature and the voltage values will increase in time, so we need to define a maximum stop voltage for the battery to stop the simulation. And for this type of battery, the 4.3 volts would be a good value. So in the model parameters, you should make sure that the initial depth of discharge is 0. For the conductive zones, we're gonna select the cell zone as the active component and the negative zone and the positive zone for the tap components. We're not going to select any zones for the busbar components as this is a single cell battery. For the electric contacts, we're going to only select the negative tab for the negative tab and the positive tab for the positive tab. And now we're ready to print the battery system connection information. As we select this, we can see that this connection info is loaded here. Now we go to the advanced option to enable the thermal abuse model. As we said, we're going to use the one equation kinetics model. It is also the option of 4 equation kinetics model. You can try it on your own. The values of alpha is 1e to the power of -6. This is a very important value and a very important parameter. You can try different alphas like 1e to the power of -5, -4, -3. These are the normal values for battery. And see how the thermal runaway conditions are going to be different. You have also the option to run the thermal abuse model only without the battery model, which means the battery model is turned off, but we're gonna run this thermal abuse model with the battery model. So now we click OK. Now we need to define the materials we need. For the aluminum, we edit this material name and the properties to define the material for the active component or the cell zone. So we name it as active material, and we give it a formula as A_M. The density would be 2092. For the UDS diffusivity, we're going to use the option of define per UDS. So for UDS 0, we're going to use a value of 1.19 e to the power of 6. And for the UDS 1, we're going to use a value of 9.83 e to the power of 5. And we overwrite the data. So the density is okay, and the UDS diffusivity is defined per UDS values. The name and the chemical formula is also okay. So we have the material here, which is a solid type material. We're gonna use it for the cell zone of the battery. So we need to define another component, another material for the tab components, which we're going to use the data of copper. So we copy the data, and now we have the copper material here. So we select it. We change the name as tab material. Give it formula as T_M. We're going to use the same density as the density of copper, but for the UDS diffusivity, we're going to use the user-defined function of battery econt MSMD bat. So we click OK. So the density is density of copper, UDS diffusivity is the user-defined function, and for the electrical conductivity, we're going to give it a value of 1 e to the power of 7. So let's check the tab material again. Okay, everything is right. So now we're gonna go to the cell zone conditions to define the material for each cell zones and the tab zones. So for the cell zone, the material should be the active material, which is already chosen. Click OK. For the negative zone, it should be the tab material. And for the P zone, or the positive zone, it should be also the tab material. So the material for the tab component and tab component of positive and negative are the same. Now we're ready to go to the boundary conditions. And for the boundary conditions, we're going to only use a heat transfer coefficient for cooling the battery. So for the wall cell zone, we're going to define a value for convection and define a value for the heat transfer coefficient and give it as 5 watts per square meters Kelvin and the free stream temperature of 300 Kelvin. So now click OK. We're gonna copy this boundary condition for the tab components, positive and negative tabs. So we're gonna click the copy and we're gonna copy from boundary zone of the cell zone to boundary zones of wall negative zone and wall positive zone and click copy. So just check if the copy operation is right. So for the convection we have a value of 5 for the negative zone. It should be the same for the positive zone. So now we're ready to define some report plots from the monitors, and from the report plots we define a new one, and from the new here and from the surface reports we select the area weighted average. We're going to report the temperature, the average temperature of the battery, which has 3 parts: the cell zone and the tab zones, and also the positive potential of the positive tab. So now we give it a name as, for the temperature, as cell temp, and from the field variable we select the temperature, it's the static temperature, and from the surfaces we select the wall cell zone, negative zone and positive zone. 3 surfaces. We report the file, report the plot and print to console and click OK. We define a new one for the potential, again area weighted average. We give it a name as phi plus, and from the field variable we select the user defined scalars. The potential phi plus is already selected, and we're going to select the wall positive zone. So we report the file, report the plot and print to console. So by defining this report of the positive potential of the positive zone, we should see how the simulation is going to be stopped at the limitation we had in the MSMD battery model, and that was the maximum voltage of the battery, maximum stop voltage, which was 4.3 volts. So in the plot we're gonna see this value as the simulation stops. And now click OK. So now we have 2 plots, the cell temperature and the phi plus. So now we're ready to initialize the solution. We use the hybrid one. But before that, don't forget that disable the flow equation, as we don't have any flow or cooling for this battery. Although we have the cooling with the method of convection, but that's not the case of solving equations for the flow, because we don't have any fluid or fluid cooling for this battery. So we don't need the flow equations. So just deselect the flow and click OK. So your simulation will run faster by deselecting the flow equations. And now we're ready to initialize the solution. So we go to run the calculation. The number of time steps would be 300. The time step size would be 0.1 second. And the maximum iterations per time step, just keep it as 10. And now we're ready to start the calculation. So as you can see, only the energy and the UDS values are iterated over time. And now we have the plot for the cell temperature and the positive potential for the positive tap. So this is gonna take a while, and after it is complete, we're gonna come back and see the results. So now the calculation is complete. You can see that almost after 11.5 seconds, the simulation reached the value of 4.3 volts for the voltage, and the simulation is stopped. So for the cell temperature, there is a gradual increase of the temperature, and for the positive potential also the same, up to 4.3 volts. We can see the contours of temperature to see the temperature variation in the battery cell. So we select surfaces like cell zone, negative zone, and positive zone. And as you can see here, almost 90% of the cell zone is covered in red, which defines the high value temperatures of about 500 degrees. And this is a good result, as it shows that most of the battery parts is above the value of 150 degrees Celsius, which was above the value for limitation for the decomposition of different parts like electrolyte or SEI or cathode decomposition. So once again, I want to emphasize on the results. As you can see, the cell temperature value goes up to 522 degrees, and most of the battery is covered with the high temperature values. The positive potential will increase up to 4.3, which was the limitation we mentioned in the MSMD battery model. And please make sure that you have included all your possible experimental or analytical data. As you saw, you can have investigations on how different parameters is going to affect your thermal abuse model, like the parameters in the one equation kinetics model in the abuse thermal modeling, and among them alpha was one of the most important ones to investigate. So this is all for this session. If you have any questions, please leave it in the comments. You can find the files, the links for the geometry creation or the mesh generation. So if you like this video, give it a thumbs up and share it with your friends. Have a good day.